Let's have a look at the glutamatergic synapse. We recognize here the presynaptic element, the axon terminal with the membrane here, and the postsynaptic element, which can be a dendritic spine, a patch of dendritic membrane, or a patch of somatic membrane, and you see here the membrane in the two layers of the membrane in black and yellow, and here is a patch of a glial cell membrane. In the presynaptic element, we recognize the vesicles that contain the glutamate, the neurotransmitter, and calcium channels here. And in the postsynaptic membrane, we recognize the glutamatergic receptor channels, NMDA, kainate, and AMPA receptor channels. Just to remind you that the synaptic transmission is unidirectional, that it's only in one direction because vesicles and calcium channels are only in the presynaptic element and glutamatergic receptors are only in the postsynaptic element. When calcium enters the presynaptic element in response to sodium action potential, so sodium action potential depolarizes the membrane to the threshold of calcium channels opening. Calcium concentration here intracellular increases very locally and transiently, and it triggers the exocytosis of a synaptic vesicle. Now, glutamate is released in this synaptic cleft, and it binds to all possible receptor sites that recognize glutamate. So it binds to receptor channels, AMPA, kainate, and NMDA, and it evokes a postsynaptic current, which is a cationic current, which depolarizes the postsynaptic membrane. But it also binds to transporters here in the glial membrane or in the presynaptic element that help to reuptake the glutamate and to insert it again in the synaptic vesicles. And also the transporters help to reuptake glutamate and to clear it from the synaptic cleft. So it means that when glutamate unbinds from the receptors, because it unbinds very frequently, it's very unlikely that it binds again to the postsynaptic receptors because it's uptaken by transporters. In summary, there are three types of glutamate receptors, AMPA, kainate, and NMDA, that are named for the agonists that selectively open them. They are all composed of 4 subunits. They are tetramers. AMPA receptors are made up of glu-A subunits. NMDA receptors are made up of glu-N subunits. And kainate receptors that we did not study here are also made up of glu-K subunits. And we did not study the kainate receptors, but they are very close to the AMPA receptors. In the postsynaptic membrane, there are 2 types of AMPA receptors, those that contain the glu-A2 subunit. This is explained in a supplement. And when it contains the glu-A subunits, it's permeable to sodium and potassium ions only, and it's not permeable to calcium ions. And these are the most common AMPA receptors. But when the glu-A2 subunit is absent, so the receptor is made up of 4 subunits, but not of the glu-A2 subunit, the channel is permeable to sodium, potassium, and calcium ions. NMDA receptor channels are permeable to sodium, potassium, and calcium ions, all of them. They are voltage sensitive due to they are blocked by magnesium ions at hyperpolarized potentials. This is also explained in a supplement. And what is explained in the supplement that we did not speak about, that these receptors open with 2 agonists. They open when glutamate binds on the glu-N2 subunit, either A to D, and when glycine also binds to the glu-N1 subunit, and this is explained in a supplement. It's a very complicated channel, 2 agonists, co-agonist, we could say, and voltage sensitive at hyperpolarized potential. And it has very slow kinetics.